Hi there. Right, first up we'll have a quick look through the knowledge and skills from lesson C 8.4. If you haven't done this lesson yet, please do go back and make sure it's completed. So we were looking at changing the concentration of reactants in a solution or the pressure of gases and looking at how that affects the rate of reaction. And you were trying to predict and explain how changing those conditions of concentration and pressure would affect the rate using collision theory. So essentially we're looking at the fact that there were a greater number of particles in a given volume, so therefore the rate of reaction would increase. And we also had a quick look at the fact that if you were to double the number of reactant particles, so by doubling the concentration or the pressure, you would double the number of successful collisions and therefore you would double the rate of reaction. So in today's lesson we're going to be looking at C 8.5 and it's all about catalysts. So there's the list of things we're going to be covering. If you wish to read them, feel free to pause and have a read, but I will be covering those again at the end. So first thing we need to talk about is what catalysts actually are. I'm sure that many of you will have an understanding of catalysts themselves, right? But your formal definition is going to be a substance that speeds up a chemical reaction without being used up. This is an important point, this without being used up, and we'll talk about that in a minute. There are numerous examples of catalysts. Here are just a couple. The first one you might have heard of, platinum and rhodium are used in catalytic converters. If you're not sure what they are part of the car exhausts. Essentially you've got your platinum and rhodium sprayed as very fine particles in a honeycomb structure for a very large surface area inside your catalytic converter, and then the unburned hydrocarbons, nasty carbon monoxide and nitrogen oxides will go in, and that catalytic converter will speed up the conversion of those gases into the less harmful nitrogen, water, vapour and carbon dioxide. Other examples, I'm sure from your biology course, you know about enzymes. Enzymes, of course, are biological catalysts. They speed up chemical processes in your body, and I'm sure you're very familiar with this kind of enzyme substrate diagram here. And most industrial chemical production is going to use catalysts. Of course, if you can use, if they don't get used up in a chemical reaction, that means you can use them many times. So if you can find a chemical that increases the rate of the production of your major product, then of course you're only going to have to buy it once. Now that does come with a bit of a caveat that over time catalysts do actually get, technical term is poisoned, so the active sites get blocked, but they are still very useful materials. So an example might be something called the Haber process, which we'll be studying in the future. It uses an iron catalyst. Just to note here, iron of course is a transition metal, as is platinum and rhodium. Transition metals are commonly useful as catalysts. And here's the equation for the Haber process. Now you can probably see the Haber process utilizes nitrogen from the air and hydrogen from water or natural gas, and combines those two to make this substance here, which I hope you might recognize, and that is ammonia. Very useful in the production of fertilizer. Oh, and why not pause the video and see if you can balance that equation. So hopefully you put a 3 in front of the H2 and a 2 in front of the NH3. Anyhow, you'll notice that iron, there it is, Fe, it's not actually written as part of the overall equation. Sometimes you won't see it written at all, or sometimes it'll be above the arrow. Basically, because you can use it again and again and again, all right, it's not going to get used up. You don't include it as part of your reactants or products. And there's a ammonia production factory just there. So catalysts, how do they actually work then? Right, first thing I would like you to do here is see if you can sketch a quick reaction profile for an exothermic reaction. Pause the video and have a go at doing that. Okay, so hopefully you have something like this. energy up the side, doesn't have to say potential, just energy up the side, reaction progress or pathway along the bottom, and then you've got your reactant energy, you've got your activation energy, remember that's the minimum energy required to break the chemical bonds, then you've got your energy released, and because it is exothermic, there is more energy released than there is absorbed in breaking the bonds, so the products are lower, and that difference you might well have labelled as delta H, and of course this arrow here is the activation energy. Okay, so how does this link to catalysts? Well, let's have a look at the next slide. Before we go there, you might want to have a little think about how that graph might look different if the reaction had a catalyst. So, I wonder if you've had a think about that. Well, here's our reaction profile diagram with a catalyst. You will notice the original reaction, here it is over the top, right, and then the catalyzed reaction here. So the catalyzed reaction clearly has a different pathway, and it is important that you mention that, a different or alternative pathway which has a lower activation energy. Right, so what that essentially means is that a greater number of particles would therefore have that sufficient energy for a successful collision, therefore the total number of particles forming the products would be larger, so the rate would increase. There you go, formally, catalysts provide a different or alternative reaction pathway that has a lower activation energy. Okay, at this point you probably might want to go and have a go at the exam questions rather than having a go at this section, because essentially it's going to be going over some of the things that we've covered very, very recently. So you need to be able to do all of these things, so go away and do your exam questions first, then come back and have a go at these. So first of all, you need to be able to define a catalyst. So pause the video and write that down. And that is something that speeds up or changes the rate of a chemical reaction, but is not used up during the reaction. Now it's interesting to note, actually, I defined it as something that speeds up a chemical reaction earlier. Technically, catalysts are actually just things that change the rate. Pretty much always you're going to be using them to speed them up, though. Right, so second one, explain how a catalyst works. So whenever you're doing an explanation, you need to be talking about activation energy and reaction profiles. So pause it and have a go. So catalysts provide an alternative reaction pathway which has a lower activation energy. Right, have a look at this diagram, and I'm sure you can probably write this down pretty quickly. I want to know what A and B represent. Pause the video. Okay, so I'm sure you realise that A is the energy released, or delta H, so that's the difference between the reactants and the products, and B was the activation energy. Right, number 4, see if you can describe in words how the graph would be different if a catalyst was used. Pause it and have a go. And I'm sure you wrote there would be a different curve, or a curve with a lower activation energy, so a lower peak. So it would start from exactly the same point here and just curve over like this. Right, final one. Which of the following could represent a catalyzed reaction? Pause the video, write down your answer. Okay, well you can probably very quickly see that the answer would be C. Why? Well, because it contains this MnO2 that is on the arrows. That doesn't get involved. It's not a reactant or a product. It doesn't change in terms of quantity. So therefore, that is going to be your catalyst. Incidentally, the first one is just the combustion of methane, so burning methane to make carbon dioxide and water. And the second one, of course, is combustion of hydrogen, so burning hydrogen to make water. Just as a little aside, this substance here, H2O2, is something called hydrogen peroxide, and commonly, well, I would normally be doing this as a practical in your lessons. So hydrogen peroxide decomposes very, very slowly to to form water and oxygen. However, if you add this manganese dioxide catalyst, manganese of course is a transition metal, that will speed up that process significantly. So you get a large amount of oxygen bubbles produced, right? So you can then use one of your methods for measuring rate using gas collection over water or a gas syringe, and you'll find that either if you've done the exam questions already, you'll find this one is in there, or if you haven't done the exam questions, go and have a go at them now. Okay, final summary slide. Let's just go over the specification statements and check everything has been covered. So hopefully you're aware that catalysts change the rate of a chemical reaction, but are not used up. This makes them particularly useful in industry. Different reactions need different catalysts, so the catalyst is specific. Enzymes are biological catalysts. Catalysts work by providing a different or alternative pathway for the reaction that has a lower activation energy. And you need to be able to draw a reaction profile for a catalyzed reaction, like we did earlier, and to be able to identify catalysts in the reactions from their effect on the rate, and because they're not included in the chemical equations. So what that means is, like that last question, right, if they are above the arrow or they don't appear at all, then they would be a catalyst. In terms of the first bit of that statement, basically they're looking at giving you data, and if a table showed that a reaction had increased in rate when a particular substance was added, that would be classified as a catalyst.